Today on How It's Made. Wind generators, putting a spin on renewable energy. PVC gloves, giving laborers a helping hand. Thermoformed glass, art that's fragile but functional. And fire trucks, we're pumped to show you how they make them. Wind generators harness the power of the wind to produce electricity. As the turbine's blades revolve, they drive a rotor that generates power. This can charge a set of batteries or even feed a transmission grid. Wind power is a renewable energy source that doesn't pollute. This type of wind generator is a recreational model, designed to power a boat or cottage with up to 500 watts of electricity. To make the propeller, they lay a template on a plank of western cedar, a rot-resistant wood that's flexible and durable, yet lightweight enough for the slightest breeze to set it spinning. After tracing, they drill a hole at each end and in the middle. Then remove the template and do a rough cut using a bandsaw. Then they put the template back, using those holes they drilled to align and secure it in place. Using a router this time, they do a precision cut. The plank of wood now has the contour of a propeller. The next step is to form the profile. To do that, they bolt the wood onto the right side of a specially designed device called a propeller carving machine. On the left side is a model propeller. After adjusting the model to the proper angle, they start to cut. As the machine's roller runs over the model, it guides a shaper to carve the wood exactly like the model. It takes about 8 passes to get the propeller's profile just right. You can see the profile well once they've marked and cut off the excess on the ends. One side is flat, while the other is curved, like an airplane's wing. Now they widen the hole in the middle of the propeller and sand off the ridges left by the carving using a low-pressure inflatable drum sander, the only type flexible enough to really get into the curves. Next, they check the balancing. Watch how a mere penny can throw off this perfect equilibrium. Finally, a coat of waterproof epoxy paint, the kind used on the hulls of boats. Now they assemble the alternator, the component that generates electricity when the propeller spins. They wrap insulation around what's called the proportional electronic regulator and install it, along with wiring, into the alternator's casing. This regulator controls the electrical charge and current. The propeller spins this rotor shaft, creating an electrical charge that sends a current from the alternator to the batteries. Once the casing's bolted shut, they mount a cooling fan on the shaft's protruding axle. This fan will expel the heat all that spinning generates. Next, they assemble the parts that make up what's called the lolly shaft, the axis on which the propeller sits. This axis enables the propeller to pivot toward the direction of the wind without twisting the wires that run to the batteries. Finally, they connect the wires from the lolly shaft to the alternator. This rubber cover protects the connection from the elements. Now they assemble what's called the propeller governor, a key component that prevents the propeller from overspinning and breaking down in high winds. When the propeller spins too fast, the centrifugal force pulls on these springs. This activates the braking flaps, generating drag to slow the propeller down. Again, precision balancing is critical, otherwise you'll have a damaging vibration. After applying the manufacturer's decal, they mount the propeller's rudder onto the back end of the wind generator's frame. On the other end goes the alternator, followed by the propeller and propeller governor, both painted black to protect the waterproof coating underneath from the sun's damaging UV rays. Polyvinyl chloride, commonly known as PVC, is a durable material similar to plastic. PVC gloves are waterproof, even chemical-proof. All kinds of laborers wear them, from commercial fishermen to oil refinery workers. PVC gloves are comfortably flexible, yet sturdy. Production begins at the cutting station with stacked sheets of cotton flannel. Using a hydraulic cutting machine and a series of dies, workers slice through some 20 layers in one fell swoop, cutting out the pieces required to make cotton gloves. Those gloves will either be sold as is or used as linings for PVC gloves. The next step is to sew the pieces together. It takes a speedy seamstress just 30 seconds per hand. Next, they sew on a wrist made of a stretchy cotton and lycra knit. This seamstress works the wristing machine so quickly, we had to ask her to slow down so that we could actually see what she's doing. Throughout the sewing process, these cotton gloves have been inside out. This next machine turns them right side in, transferring them onto a heated hand form. The machine then presses each glove onto the form. The gloves drop down to a conveyor belt below. It transports them to a worker who inspects them and pairs them up left and right. Elsewhere in the factory, meanwhile, workers prepare the PVC solution. The recipe varies according to the glove model, but generally consists of coloring and 5 to 8 different chemicals. They add an antibacterial, antifungal solution to combat odor from hand perspiration. To apply the PVC, workers slip a metal form into the thumb of each lining, then put the lining onto a thumbless hand form. If the hand and thumb forms were one piece, it would be difficult to remove the stiff PVC glove afterward without tearing. The linings go through what's called the singer, a propane flame that burns off any dust or loose threads. Then it's into the PVC bath. The basin of liquid PVC moves upward, coating the liners. As the basin descends, the excess drips off. Then the gloves go for a spin under infrared lamps for 45 seconds. The spinning spreads the PVC uniformly so that it doesn't accumulate on the tips of the fingers, forming clumps. The heat ensures it dries evenly. After a second coat, the gloves pass through a propane-fired furnace for about 20 minutes at 190 degrees Celsius, then through a cooling chamber for 5 minutes. For glove models with extra strong grip, They blow PVC chips onto the first coat of PVC while it's still wet. When the gloves go through the furnace, the heat embeds the chips. After cooling, the gloves are dried and cured and ready to handle a hard day's work. Decorative glass objects can be blown or thermoformed, two very different glass-making techniques. In glass blowing, the artisan shapes hot glass by rolling it and blowing air into it. Thermoforming is more of a molding process, better suited for making flat objects. When you look at these magnificent pieces, it's hard to believe they begin as run-of-the-mill window glass. It comes in ready-made panels in thicknesses ranging from 3 to 10 millimeters. The first step is to measure the overall dimensions of the glass panel, then divide it into pieces, each slightly larger than the object it will become. They'll turn this panel into large decorative plates, so they divide it into 3 squares, each about 35 centimeters in diameter. They place each square over a paper pattern. Using a glass cutter, they score the shape of the plate. Then they apply pressure with a rubber mallet to separate the glass along the score line. They cut away the excess, breaking it off with a few gentle taps. Now they position the plate-shaped glass over a drawing and begin the artwork. First, tracing the outline. Now they embellish the design and fill in the details. They use enamel paints specifically designed for painting on glass. Once the brushwork's done, they use a paint gun to apply the background colors and shading. The glass has been cut and decorated, but it's still perfectly flat. So the final step is to mold it using extreme heat, hence the term thermoformed. The mold they use is made of fireproof materials designed to withstand high temperatures inside the oven, known as a kiln. They carefully lay the glass over the mold. They mold several different pieces at the same time. In the intense heat of the kiln, the glass will melt and take on the exact shape of the mold, right down to the most intricate textural detail. These small pieces of glass will become the paint pots on this glass replica of an artist's palette. It takes an hour and a half for the kiln temperature to climb to a scorching 843 degrees Celsius. At peak temperature, they open up briefly to make sure that everything is progressing well. The glass at this phase should be the consistency of maple taffy and glowing bright red. If it is, they can close the kiln and begin the cooling phase. 6 hours later, the glass pieces have hardened into the shape and texture of their respective molds. These plates and spoon rests and other pieces are cool enough now to come out of the kiln. The beauty of thermoformed glass lies in the striking combination of transparency and vibrant color. Add to that the endless shape possibilities, and you've got truly functional art. There are different types of fire trucks. Pumpers hook up to fire hydrants, boost the pressure, then shoot the water out through hoses. Ladder trucks elevate firefighters on either a ladder or a platform. Rescue trucks have tools to cut through metal and clear obstructions. Early firefighters couldn't do much more than pass buckets of water from man to man. The 1720s saw the arrival of wagons carrying water tanks and hand pumps. Those newfangled pumps could spew out an impressive 60 gallons of water per minute, about what you get from 2 garden hoses. The first horse-drawn fire trucks with steam-powered pumps went into service in 1852. Gas-powered trucks replaced them in the early 1900s. This pumper truck can deliver 6,000 liters of water per minute. Mechanical engineers usually custom design fire trucks to suit the particular needs of the fire department placing the order. The truck's body is made entirely from 4-millimeter thick sheets of marine-grade aluminum. Following the technical drawings, workers cut the aluminum panels to the sizes required, notching certain corners at a 90-degree angle. Workers weld the pieces together to form what's known as the crew cab. The crew cab not only carries the firefighters, it also houses the control panel for the water system. Meanwhile, other workers measure and then cut pieces of aluminum to build the subframe that will support the crew cab from underneath. They weld the parts together. Installing the steps, workers leave a gap of about 1.5 centimeters to enable water to drain down. They line the storage compartments with aluminum sheets, using a sander to make textured circles on the smooth surface. This pattern will camouflage the scratches that moving equipment in and out will inevitably create. They use a machine called a press brake to bend the sheets to the required shape. Then, using what's known as a punch press, they cut holes for the built-in lights, the door handles, and the various control knobs. Workers now assemble the pieces and make any necessary adjustments before painting rather than after to avoid damaging the finish. After this fine-tuning, they'll disassemble everything and send the parts to the paint department. After that, they'll put it all carefully back together. The full-scale assembly can now begin, starting with the water pump. It arrives here ready-made from the supplier. Next comes the crew cab. This one isn't for the pumper, but rather for a yellow rescue vehicle. The pipes that lead to and from the water pump go into a threading machine. The pipes are part galvanized steel, part stainless steel. Once they're threaded, they're ready to be screwed into the pump's water outlets. The drive shaft, that long piece coming from the transmission, doesn't just perform its usual job of turning the rear axle when the truck is in motion, it also powers the water pump when the truck is parked fighting a fire. This control box runs the fire truck's electrical system, including the flashing emergency lights. Each wire is color-coded, number-coded, and function-coded. Workers run the wires from the box to the control panel in the crew cab. Then they hook up the odometer, speedometer, and other dashboard indicators. They install water pressure gauges, adapters for connecting the hoses to the water system, and pressure release valves for adjusting water pressure. Lo and behold, a shiny new fire truck built to a department's exact specifications. Only there's one thing the client didn't have to specify, that it be painted fire engine red. Today on How It's Made. Fresh cut flowers, combining nature and nurture. Adhesive tape. We'll stick to the facts on this one. Tofu. Making the bland grand. And lottery tickets. Sometimes a winner, but always a gamble. To wish condolences, congratulations, or for romance, there's no shortage of customary occasions on which to send flowers. Whether made up in a splendid arrangement or simply placed in a vase, fresh-cut flowers rarely go unappreciated by the recipient. Roses are a perennial favorite. Florists buy them from commercial greenhouses. Those greenhouses have sophisticated sprinkler systems positioned to irrigate the soil rather than the plants, because watering directly on the rose bushes would grow harmful fungus. The hotter the weather, the more watering, up to 7 times daily for about 5 minutes each time. The greenhouse climate is computer controlled. If it gets too humid, the computer automatically triggers the roof to open, bringing down the temperature. The ideal greenhouse temperature for most flowers is about 23 degrees Celsius during the daytime and 16 degrees at night. With every watering, the roses get a low-level dose of fertilizer, the botanical version of taking a daily vitamin supplement. It's a mix of nitrogen, phosphate, and potassium, the proportions determined by ongoing soil analysis. If the pest specialist detects a bug problem, he applies an insecticide treatment to target that particular pest. But first, they close the roof so as not to pollute the outside environment. Workers handling the chemicals wear masks and protective clothing. The roses grow through the openings of horizontal trellises positioned one above the other. This ensures the stems grow tall and straight. Crooked roses, after all, are worthless. Cutting the roses is tricky and prickly. Workers have to wear thick gloves to protect against the thorns. They cut the stem at a 30 to 45 degree angle just above the second set of 5 leaves. The cut must be precisely at that spot for a second rose to bloom, about 40 to 55 days later, depending on the season. Growth is slower in the winter because there's less sun. The growth period also varies somewhat according to the variety of rose. The fresh-cut roses go into a bucket of lukewarm water with a few drops of bleach to kill off any harmful bacteria. Workers then check each and every rose to make sure the blooms and foliage are free of defects. Then they classify the roses by length. The longer the stem, the more the rose is worth. They make a bundle of each length. Then trim the bottom of the stems to equalize the height. They wrap the roses in newsprint so they won't dry out during shipping. The transport trucks are refrigerated in summer and heated in winter to keep the roses at a safe temperature, about 6 degrees Celsius. To make a bouquet of dried roses, they select open blooms for a nicer look, then hang them upside down in a room cooled by fans. They leave lots of space between bouquets so the air will better circulate. The roses take a week to dry out. Fresh-cut flowers are striking, whether part of an arrangement or in a vase. They can last in water for about a week, provided you trim a centimeter off the stems to open up the water channels, fill the vase with lukewarm water, never cold water, pour in a bit of bleach to ward off stem clogging bacteria, change the water every 3 days, and be sure to keep the flowers away from the heat of a sunny window. Adhesive tape was invented in 1925 as a painter's masking tape for auto body shops. That led to transparent tape, designed to seal the cellophane wrap used by the food industry. Then tape was introduced as a household item, and the idea just stuck. These rolls of plastic film, called polypropylene, are on their way to becoming shipping tape. The rolls go on a machine called the unwinder. Workers then position a strip of adhesive splicing tape along the end of each roll. This will enable them to connect one roll after another, creating an uninterrupted feed to the production line. Now watch closely. Once a roll unwinds completely, its end sticks onto the splicing tape at the beginning of the next roll. Once that roll's unwound, its end will stick to the beginning of the next, and so on. An automatic tension adjuster ensures that the machine pulls the film evenly to prevent ripping. The unwinder also applies a solvent to the film surface. This prevents the film from sticking while unrolling. To transform this film into tape, they coat one side with a hot adhesive known as hot melt, made from several ingredients. Synthetic rubber gives it flexibility. A UV protector keeps it from drying and discoloring, while an antioxidant prevents aging. Synthetic resin makes it sticky, while pigmentation oil provides a choice of colors, in this case, tan. They load the hot melt into a preheated holding tank, which maintains it at a piping 200 degrees Celsius to keep it from hardening. The tank pumps the adhesive to a machine called the gluer. They wipe away the excess, then roll the film. And there goes the adhesive. A cooling roller, that black one on the top, immediately hardens it. A computerized sensor ensures there's an even coat of adhesive. If not, it automatically signals the pump to adjust the output. Now, a machine called the rewinder rolls the tape onto spools. Remember the unwinder that spliced the rolls together? Well, the rewinder unsplices them. When a spool fills, a knife separates the tape at the splice point so that winding can begin on the next spool. The tape on just one of these spools would run the length of 85 football fields. The spools feed a row of sharp razor blades called the slitters, which divide the 1.5 meter wide tape into several strips. Shipping tape is 48 millimeters wide, so they get 31 strips per spool. Each strip winds onto a cardboard core, its end sealed with a tab. The length of tape per roll varies according to the customer's specifications. As the machine ejects the finished tape rolls, in comes the next batch of cardboard cores. Then it's off to the packaging department. Nothing's shipped out, however, before a quality control check. They test a sample roll from each spool. In one test, they unroll the tape sticky side up, then release a tiny stainless steel ball down an incline, measuring how far the ball rolls before it sticks and comes to a stop. To pass the test, the ball has to adhere within a certain distance. The stopping distance varies depending on the type of adhesive tape. Some people just can't get past that rubbery texture, but tofu enthusiasts say it's all in how you prepare it. Tofu is a great source of protein, low in saturated fat and cholesterol-free, and it's versatile, absorbing whatever flavors surround it. Tofu is made from soybeans, the seeds that grow in the pods of the soybean plant. They contain 40% protein, more than double the protein in beef or fish. They start by soaking the soybeans in cold water for 18 to 24 hours, depending on the season. In winter, beans are stored in outdoor silos and take time to warm to room temperature. Here's what the beans look like before and after soaking. As they absorb the water, they double in size and soften up a bit. The bloated soybeans go onto a conveyor belt, where a rotating device transports them to a crushing machine. The machine crushes them into a thick and grainy soup of soybean milk and pulp. It does this by forcing the beans through a filtering screen. Next, they transform the soup into a paste by heating it in a steam cooker for 3 to 4 minutes. Then it's into a centrifuge machine. As the chamber spins, the centrifugal force separates the milk and pulp. The milk passes through a cone-shaped filter, while the pulp, called soy meal, sticks to the sides of the chamber. The soy meal goes off to be sold for cattle and pet food. The milk stays behind to be transformed into tofu. Still piping hot, it goes into a coagulation tank to be thickened into curd. But first, they add different herbs and spices because this batch will be sold as flavored tofu. Then they add the coagulant, magnesium chloride, along with water to activate it. Then more stirring. It takes about 15 minutes for the soybean milk to congeal into soybean curd, otherwise known as tofu. When it's ready, it's still steaming but pretty soggy, so they run it through a perforated cylinder to drain as much liquid as possible. By the time the tofu comes out the other end of the cylinder, it's relatively dry and roughly the consistency of scrambled eggs. Now it can be processed into those familiar blocks you buy at the supermarket. They transfer the tofu into large rectangular molds lined with cheesecloth. Then it's into a press that applies 59 kilograms of pressure. This squeezes out most of the remaining liquid and molds the lumpy, loose tofu into a firm rectangular block measuring 38 by 74 centimeters. They cut the block lengthwise and widthwise into 54 blocks of 300 grams each. Tofu itself is pretty tasteless, But like a sponge, it absorbs the flavor of whatever it comes into contact with. They drench this batch in a spicy marinade to make jalapeno-flavored tofu. After verifying the weight of each block, they package the tofu with a sprinkle of spices for garnish. Then, to kill off any bacteria, the blocks go into a pasteurizer at 110 degrees Celsius for an hour. When they come out, they drop into a cooling basin, into water just above freezing temperature. They stay submerged for about an hour. Tofu comes either pre-flavored or plain. It also comes in different textures. Firm tofu maintains its shape in soups and stir-fries, while soft tofu and silken tofu are ideal for blended dishes and desserts. The odds of winning big in a lottery are slim, to say the least. Still, we keep hoping that lottery ticket will become our one-way ticket to extreme wealth. Experts say your odds of picking the winning numbers never change, no matter how many people buy tickets. Lotteries are by no means a modern invention. The emperors of ancient Rome held them for entertainment. European monarchs used state lotteries to help fund their extravagant lifestyles, and the American colonies held lotteries to finance roadwork and construction projects. Pressure from the church and widespread fraud led many countries to ban lotteries during the 1800s, but governments eventually reconsidered. They just couldn't resist milking that cash cow. Those eye-catching tickets are designed by graphic artists. A technician takes the design, separates it by color, then sends the information to a machine called an image setter, which generates one negative per color. Next, they place the appropriate colored film under each negative and expose it to ultraviolet light. This hardens the color not shielded by the dark portions of the negative. When they wash away the unhardened color, they're left with a color image. They layer the films to make the client a mock-up of the finished lottery ticket, in this case a scratch-and-win type. Now they make the printing plates, one for each color of the design. First, for the non-playing area, everything outside the scratch zone. Each negative goes onto a paper-thin aluminum plate coated with a UV-sensitive emulsion. They expose the plate to UV light for about 20 seconds. This hardens the unshielded emulsion. The rest is washed away in a chemical bath, leaving the design in relief on the plate. For the ticket's playing area, the same process, but instead of an aluminum plate coated in emulsion, they use one made of photopolymer, a light-sensitive plastic. The finished plates are now ready to go onto the printing press. Their raised surface will work just like a rubber ink stamp. The non-playing area goes on first. This method is called offset printing. The press applies up to 9 different colors, one after another, from lightest to darkest. High-intensity UV lights dry the ink in the mere half-second between color applications. Next comes the playing area. A high-speed inkjet printer first applies the game numbers, chosen randomly by computer. Infrared lamps dry the ink in a split second. A strobe light enables the press operator to do spot checks as the tickets whiz by at a rate of 5 meters per second. Then the printer gives each ticket a unique barcode. This enables ticket vendors to scan your ticket to see if you've won. It also shows whether a winning ticket is genuine or a forgery. The next machine seals the game numbers with layers of varnish, then applies 6 coats of scratchable ink. An electronic scanner checks the positioning of the scratchable ink, making sure it hides the numbers. The first 3 scratchable ink coats are black. The next 3 white. All those layers to keep cheaters from holding the card up to the light to see the numbers. Now they can finally print the playing area design onto that white background. In this case, a crossword design. A machine now perforates the rolls of tickets so they can be folded. It processes 3 meters of tickets per second. Here's what that looks like in slow motion. The next machine folds the tickets along the perforation lines into piles called fan folders. Goodbye slow motion. Here's the actual speed. Before the lottery tickets are shipped out, several samples undergo a quality control inspection. The company checks that the tickets are properly printed, and it performs a series of scratch tests and chemical tests to make sure they're absolutely cheat-proof. Today, on How It's Made. Car radiators. They keep their cool, automotively speaking. Hatchery chicks. This segment is guaranteed to lay an egg. Phyllo dough. We visit a bakery that's wrapping up production. And cross-country skis. There's no business like snow business. When the gasoline in a car engine burns, up to 70% of the energy generated converts into heat. A lot of this heat goes out the exhaust system, but much of it stays, heating up the engine. The car's cooling system prevents overheating. The system's key component is the radiator. A water and antifreeze mix absorbs the heat generated by the engine. The fluid then flows through the radiator's tubes to cool down. The tubes are made from paper-thin brass. Rollers bend the 4-centimeter wide strip into the shape of a flat tube. The tubing then runs through a vat of bubbling hot molten lead. As the tubing exits the vat, it runs through cold water that hardens the lead coating. A cutter then chops the tubing into pieces, the length of which varies according to the model of radiator. These are about 76 centimeters long. Meanwhile, another machine shapes a narrow strip of copper just 1.5 millimeters thick into what are called cooling fins. As we'll see in slow motion, the machine folds the copper strip fan-like, then perforates it, creating mini air vents. When the hot fluid runs through the tubes, these fins will transfer the heat to the air flowing through the radiator. The cooled fluid can then go back for another round of absorbing engine heat. The cooling fins come out of the machine cut to size. Then workers manually stack the tubes and fins one on top of the other. They straighten them out, then apply a brass tag indicating the model number and date of production. Then they compress and strap the components together. Elsewhere, a computer-guided machine punches out a pattern on brass sheets. These will become what are called headers. There's one on each side of a radiator. The punching tool then changes to a knife, which now cuts along the perforation lines. Using a press, they bend each header, then punch slots for the radiator's tubes. Now, using a mallet, they hammer the headers onto the ends of the tubes. The banging inadvertently closes a few tubes, so they use a special roller to reopen them. After cleaning the surface, it's into an oven at 315 degrees Celsius. In just 2 minutes, the lead melts, fusing the tubes and cooling fins. After straightening out any crooked tubes, workers dip the headers in a tank of hot liquid lead for 30 seconds. This solders them to the sides of the radiator. They apply a few drops of lead on the corners for reinforcement. The headers and tube openings are now encased in lead. Workers now feed a sheet of brass into a press to form the tanks that go onto the headers. One contains a brass tube. Hot transmission oil enters one end of it and exits the other, cooling along the way. Once workers finish welding the tanks to the headers, they solder on what's called the filler neck, a spout for pouring antifreeze into the tank. On the opposite tank, they weld on a water intake pipe. This will be the entry point for the fluid heated by the engine. Finally, they coat the finished radiator in an asphalt-based black paint. The asphalt content makes the paint heat resistant and protects the radiator's cooling fins. Which came first, the chicken or the egg? It's an age-old question, and we can't give you the definitive answer, but we can take you to a hatchery to see how baby chicks are bred. It's the first step in commercial chicken farming, or the second step if you think the egg came first. Chicks come from eggs fertilized by mating, but a hen can lay eggs without mating. Those unfertilized eggs are the ones we eat. The fertilized ones go to the hatchery 3 or 4 days after being laid. Hatchery workers transfer the eggs onto special trolleys, then roll them into the incubator, where the temperature and humidity level mimic natural conditions. The egg yolk, egg white, and shell all nourish the embryo. Every hour, the trays shift 45 degrees to the opposite side and back, simulating how hens turn their eggs while waiting for them to hatch. After 18.5 days, the eggs come out of incubation and go on to a conveyor belt. They pass under an infrared sensor that detects any whose color is too transparent. These are unfertilized eggs that slip through. The sensor triggers a suction device to remove them. They go to a rendering plant to become animal feed. The fertilized eggs continue along to the next station to be vaccinated against Marek, a poultry disease. Automated needles pierce a hole in each shell and inject the vaccine into the amniotic fluid surrounding the chick. Now a suction device transfers the eggs to hatching trays, 168 eggs per tray. About 150 of them can be expected to hatch. The rest died in incubation or have physical defects. Day 19. The chicks use their beaks to crack a hole through the shell, then a horizontal line all around. After 6 to 8 hours, the chicks finally emerge from the shell. They're covered in short feathers called down, and they're able to walk and see. After about 4 hours, their down has dried. Now workers roll the chicks to what's called the separator, a machine that separates the birds from the shell halves. The shells are larger than the chicks, so they stay on top while the chicks fall down to a conveyor belt below. The shells, which are high in calcium, go to a rendering plant. The chicks move on to be classified according to gender. Workers put the females down one chute, the males down another. They determine the sex by checking 2 rows of feathers. If one row is shorter than the other, the chick's a female. If the rows are the same height, it's a male. Each chute feeds a separate conveyor belt. An optical counter tracks the number of males and females. The chicks now fall into specially designed transportation boxes, 102 chicks per box. Some clients request that their order of chicks be vaccinated against bronchitis. Those boxes pass under an aerosol sprayer that sprinkles them with a mild dose of vaccine. Poultry farms raise chicks for either meat or eggs. Females used for egg production begin laying eggs at about 20 weeks of age. For meat production, females reach slaughter weight in about 38 days. Males, depending on market size, take from 40 to 65 days. If you like Greek food, then you've probably tasted baklava. It's made with a paper-thin, flaky dough called phyllo, the Greek word for leaf. Phyllo dough itself is low-fat and cholesterol-free. Unfortunately, the stuff they usually fill it with isn't. Phyllo dough can be made by hand or by machine. Either way, it starts with the same dough recipe. The proportions are roughly 40% water to 60% flour. They use 2 types of wheat flour, high-protein flour to make the dough strong and flexible, and low-protein flour to make its texture smooth. They also add sorbate, a preservative, to increase shelf life. After about 15 minutes of mixing, the dough is ready. They cut off a section and feed it into a machine called the divider, which transforms it into a cylindrical wad. They hand roll the wad into a rough ball, then feed it 2 or 3 times through a machine that kneads the dough into a rounder, harder ball with no air bubbles trapped inside. They can tell when it's ready just by feeling it. Then a machine called the sheeter flattens the ball into what looks like pizza dough. Workers stack about 30 sheets with craft paper in between to absorb some of the moisture. Now, the key step, opening the dough. First, they lay a large cotton cloth over the work surface. It must be 100% cotton to absorb the moisture. Otherwise, the dough would stick together. They take a sheet of dough and begin stretching it by hand until it's approximately 2.5 meters square. Even though the dough is stretched thin, it doesn't tear. This is due partly to its protein content and partly to the skill of the worker. They repeat the process with all 30 sheets, stacking them one on top of the other. Then they take a plank of wood, called a sanida in Greek, and roll the dough sheets onto it one by one, removing the cloths that were in between. They sprinkle cornstarch on the dough, just enough to prevent sticking. Too much cornstarch will burn the dough. Now they move the sanida to another table and cut along one side of the dough. They remove the wood and open the sheets flat. Then they cut rectangles measuring 33 by 43 centimeters, standard phyllo size. Each sheet of phyllo dough is about as thin as a sheet of tissue paper, but it's strong and flexible enough not to tear when a baker works with it. Machine-made phyllo dough is a much faster method used primarily for mass-produced frozen food items. An automated machine called the stretcher transforms a big wad of dough into a thin, flat sheet, applying just the right amount of cornstarch. A continuous air current coming from underneath creates an air bubble. The height of the bubble tells them whether the dough is the right consistency. The dough dries under infrared lamps. This step is necessary because this method doesn't use craft paper and cotton cloths to absorb the excess moisture. The dried sheet of dough rolls onto a spool. They cut along the side to release the dough and lay it flat. Using a template, they cut the standard size rectangles, yielding 800 sheets of phyllo. They roll about 20 sheets together at a time and wrap them in plastic. Then they vacuum pack and heat seal the package. Phyllo dough stays fresh for 6 weeks in the refrigerator, 6 months in the freezer. Cross-country skis used to look pretty much all the same: long, narrow, and wooden. Today's skis, however, come in many different styles, specifically designed for the many types of cross-country: telemark, backcountry, all-terrain, touring, and racing. Archaeologists in Scandinavia have uncovered ski artifacts 5,000 years old. These Stone Age skis had enabled people to hunt during the winter. Skiing became so vital a means of transportation that the Vikings worshipped a god and goddess of skiing. 19th century Scandinavian soldiers wore skis in winter warfare. They held races in their spare time, turning cross-country skiing into a popular sport. From there, it just snowballed. One way to make cross-country skis is compression molding, a process that uses heat and pressure to bond the components together. First, a computer-guided blade cuts out what will become the ski's underside, called the gliding surface. It's made of pre-assembled fiberglass laminate and polyethylene thermoplastic, a friction-resistant material. They lay it into the bottom half of a mold, then glue on steel edges for grip. This spray makes the adhesive dry faster so that they can apply the principal adhesive, epoxy. A rubber shock absorber goes on the back, followed by a durable plastic reinforcement called the heel piece protector. The ski's wooden core is made of aspen and birch laminated together. Next comes a sheet of fiberglass impregnated with epoxy for extra reinforcement. The wood core is now sandwiched between 2 high-resistance layers. Then for decoration, a plastic film with a silkscreen design. With everything now in the bottom half of the mold, they can clamp on the top and tape it up to ensure nothing shifts out of place. Then it's into a press that compresses the mold and heats it to 85 degrees Celsius. This activates the epoxy, hardening it in 12 to 15 minutes, depending on the thickness of the ski. Now they do a rough cut to trim off the excess. Then they sand all the edges until they're smooth. They run just the gliding surface across a grinding stone, that white object you see below. This extra step is only for the higher-end models. Another way to make cross-country skis is by a process called reaction injection molding. First, they place the ski's top layer, a fiberglass epoxy sheet, in the mold. Then the gliding surface, made of pre-assembled fiberglass laminate and polyethylene with a high-resistance backing. Instead of a wooden core in the middle, this press injects a super-resilient plastic. In just 3 seconds, the injection phase is over and the reaction phase begins. This demonstration shows what happens. First, the polyurethane inflates. Then, it hardens. After 8 minutes, it's hardened enough to come out of the mold. They let the ski cure for up to 8 hours, at which point it's strong enough to support the weight of a skier. So now these 3 components, the top layer, the polyurethane middle, and the gliding surface, are one. Now comes the finishing. First, they trim and bevel the edges. They sand the gliding surface. Then they carve a groove down its length. This gives the ski directional stability. All that's left to do now is decorate the skis. First, the background color in a quick-drying, solvent-based lacquer. They apply the design manually, one color at a time using the silk screening process. A typical design consists of 5 to 7 colors, including the background. To keep the skis looking vibrant, they protect the paint with a coat of transparent varnish.